In this lecture, I am going to introduce gear trains. We will discuss about simple and compound gear trains and calculate the motion and torque transmission ratios. What is a gear train? A combination of gears used for motion transmission from an input to an output shaft. This is a gear train. There can be combination of different types of gears. For example, you can have spur gears, bevel gears, and combination of them. We classify gear trains as simple, compound and epicyclic or planetary gear trains. In a simple and compound gear train, all the center of rotation of the gears are fixed. We are going to look at examples and understand this. While in an epicyclic gear train, some gears will have their centers which are moving, which are rotating. Let us start with this simple gear train and try to calculate the gearing ratio. As I have mentioned, in a simple gear train, the center of rotation of all gears are fixed, and in a simple gear train, each shaft carries only one gear. So, let us look at an example. Here is an example. We have this input, this is the input gear and output gear, all these centers are fixed. Now, if you recall the motion transmission ratio, let us say for this pair of gears A and B. So, omega B divided by omega A is minus of N A by N B, where N A and N B are the number of teeth on gears A and B respectively, and the negative sign indicates the direction, they are in opposite directions. Now, if you continue this for the pair B and C and for C and D, then you have these three transmission ratios for these individual pairs. Therefore, if you want to find out the transmission ratio from the input to the output, which means we want to find out omega D by omega A, that can be obtained by multiplying these three ratios, and if you do that, you will finally obtain minus of N A by N D. The other terms will cancel off. So, this is what I write here finally, omega D by omega is minus of N A by N D. So, this is a simple gear train. Each shaft carries only one gear. Let us now look at the torque transmission ratio for a simple gear train. Here I have also introduced the gear box. The reason for this will become clear very soon. Now, from the power balance, this we have been using and you have used it previously to calculate the force transmission. Here I am using the power balance equation. So, the net rate of work done on the system is 0. There are two sources through which work is being done, one is at the input, the other is at the output, and if you do this power balance, then you get tau A omega A plus tau D omega D equal to 0. Here we initially do not know the direction of tau D. If you recall the gearing ratio between A and D, which we have just now derived, which is minus of, so omega D by omega A is minus of N A by N D. If you substitute this here, then tau A omega A plus tau D. So, omega D is minus of N A by N D times omega A. So, that is equal to 0. So, that tells us tau d is equal to tau A n d by n A. Omega is not equal to 0. So, we have this relation between torque at the output and the torque at the input. So, tau d is equal to tau A n d by n A. So, this is what I have written out for you. Okay. So, this is our torque transmission ratio. In general, this n d by n A is not equal to 1. Therefore, tau d is not equal to tau A. Now, why are we discussing this? If you look at the equilibrium of the whole system of this gear train, then we have two torques acting on the system, tau A and tau d, which are not equal. So, therefore, system cannot be in equilibrium, it cannot be in equilibrium unless there is an external torque acting which keeps the whole system in equilibrium, and that comes from the gearbox. This gearbox is fixed onto certain base, it has got its foundation, it is fixed onto onto the ground, and it is not allowed to rotate or move. Now, this fixation therefore introduces another torque which is tau g b, which I call tau g b. Now, with this the whole system must be in equilibrium. So, moment equilibrium tells me that tau A plus tau d plus tau g b must be equal to 0, of which I know tau d in terms of tau A, which I substitute, and finally, I can calculate the torque that acts on the gearbox. So, the gearbox foundation has to take this torque. Now, let us go over to a compound gear train. When a shaft contains more than one gear, then the gear train is called a compound gear train, and the axes are of course fixed, as we have discussed. This is an example of a compound gear train. Now, here we have two gears, one is this, the other is this. This will be more clear in this schematic diagram. So, there is this shaft which carries two gears fixed to it, both the gears are fixed to this intermediate shaft. There are two meshing gears like this is between the input and one of the gears on the intermediate shaft, and here is the other meshing to the output. Now, let us try to calculate the transmission ratio. We proceed as we have done before. So, omega b by omega A is minus n A by n B. Now, omega b and omega c are same because they are on the same shaft. So, omega c is equal to omega b, and finally, omega d by omega c is minus of n c by n d. Now, if I want omega d by omega A, then I use these three relations, and we can easily arrive at this transmission ratio omega d by omega A. Now, that is a product of these two ratios n A by n B and n C by n D. Here they do not cancel off, as in a simple gear train the intermediate gear tooth, the number of teeth they cancel off. Here they do not. This is a compound gear train. Let us look at the torque transmission ratio for a compound gear train. Once again we start with the power balance as I have written out here, and we have that gearbox again for the same reason we have discussed before. Now, the motion transmission ratio we have just now derived, and if I substitute in the power transmission, then I have the torque at the output in terms of the torque at the input. So, these are very simple calculations. Now, once again the torque tau A and tau D, they are in general not equal. So, therefore, we require an additional torque for equilibrating the whole system, which is the torque on the gearbox from the foundation of the gearbox. Now, if you use the moment equilibrium equation, then that relates tau A, tau D and tau G B, and that sum must be equal to 0 for equilibrium. You can substitute tau D in terms of tau A and calculate tau G B in terms of tau A. So, that relation gives us how much torque has to be resisted by the foundation of the gearbox. So, that completes our discussion. Basically, what we have done is we have introduced gear trains. We have looked at two types of gear trains, simple and compound. We have calculated the motion transmission ratio and the torque transmission ratio. So, with that I will close this lecture.